and are listening. Today we are going to see Unit 5 Laplace Transform of Engineering Mathematics 2. And this is Dr. S. Ramya presenting for you. Before we get into Laplace Transform, here I am sharing a link. Spare a few minutes to watch it. A simple example has been considered by the presenter to explain the need of signal processing, which is possible only through transformation. Transformation or transform is nothing but changing from one form to another. A system of sound is converted as signals and modeled in a time domain, and the unwanted noise included in it can be removed by converting the signals in time domain to frequency domain using the transformation. Signals can be represented as a mathematical model in time domain, which in turn transformed into frequency domain. As the signals are separable in frequency domain, using transformation we can eradicate the unwanted noise and process the signal. Thus, transformation plays a vital role in our day-to-day life. Transformation can be basically classified into two types, discrete and continuous. Discrete time signals are processed using discrete transformation, and continuous time signals are processed using continuous transformation. Laplace transform is one such continuous transformation. Before we proceed into Laplace transform, let us see what is integral transform. An integral transform is any transform I of the following form: I f of u is equal to integral a to b f of t k of t comma u dt. The input of this transform is a function f and the output is another function I f. The function k of t comma u is called kernel of the transformation or integral kernel. By defining this kernel in different ways, we get different types of integral transform. Laplace transform is one such transform. It was given by the French mathematician Laplace, and it is defined as a function f of t. If it is defined for all positive values of the variable t, then its Laplace transform is denoted by L of f of t or capital F of s, and is defined as integral 0 to infinity e power minus st f of t dt. Proceed to next see the sufficient condition of the Laplace transform. A function f of t is said to have Laplace transform if it satisfies the following conditions: piecewise continuous, exponential order. Next, we proceed to see the definition of piecewise continuous function. A function f of t is said to be piecewise continuous if it have only finite discontinuities in the given function. F of t is said to be of exponential order if limit t tends to infinity e power minus st f of t is equal to 0. A function f of t, if it satisfies these two conditions, then its Laplace transform exists. We will now proceed to see an example to understand the Laplace transform better. Find L of f of t if f of t is equal to e power t for 0 less than t less than 1 and 0 if t is greater than 1. My function f of t is a piecewise defined function. By definition, L of f of t is integral 0 to infinity e power minus st f of t dt. The interval 0 to infinity is split into 0 to 1 and 1 to infinity as per the definition of my piecewise defined function. In the first part, the function takes the value e power t, and in the second part, the function takes the value 0. Hence, the second integral becomes 0. Evaluating the integral and substituting the limits, we get the answer. Next, we proceed to see an important property, linearity property of Laplace transform, which is a very basic and fundamental property, not only for Laplace transform but for any kind of transforms. And the property is that if L of f of t is equal to f of s, then L of a into f of t plus or minus b into g of t is equal to a into capital F of s plus or minus b into capital G of s. And the proof is based on the definition of Laplace transform. And since Laplace transform is an integral transform, its definition is based on integral, and we all very well know that integration satisfies linearity property. That is, addition or subtraction combination. If we have function, we can split the function and we can integrate it term by term. And also, if we have any constant multiplying, then we can take out the constant and integrate the function. Using the property of integration and definition of Laplace transform, L of a into f of t plus or minus b into g of t can be written as integral 0 to infinity e power minus st, and the function is a into f of t plus or minus b into g of t. Next, using the property of integration, it can be split into two integrals: 0 to infinity e power minus st a f of t dt plus or minus integral 0 to infinity e power minus st b into g of t dt. Taking out the constants, the integral can be written as a into 0 to infinity e power minus st f of t dt plus or minus b into 0 to infinity e power minus st g of t dt. Here the first integral represents nothing but Laplace transform of the function f of t, and the second integral represents nothing but the Laplace transform of the function g of t. Hence it can be written as a into capital F of s plus or minus b into capital G of s, and that ends the proof of the property. Thank you very much for watching the video. In our next lecture we will see some standard functions, Laplace transform of some standard functions.